we have built a one-time password infrastructure for ourselves, and it involves, there's lots of pros and cons of doing different things. I'm going to talk about the process we went through in our decision making and what we ended up building. It's not necessarily a solution for everyone, but I think it helps you think about, helps give you an idea of the sorts of things you need to think about. So a little bit about the context of where we are and what's important to us. This is LIGO. LIGO is the Laser Interferometer Gravitational Wave Observatory, which is a really cool title that never fits on a name badge. It's a facility, we're building a facility that to detect gravitational waves, which will be the final confirmation of Einstein's last unproven prediction. So it's really cool science, Nobel Prizes will be awarded, et cetera, et cetera. But it makes this interesting in some interesting ways. So one of the things that actually makes it interesting to authentication for us is the simple one, we're distributed. Okay, our instruments are in 2 different states. In addition, they're operated by Caltech. Owned and operated. So we have a facility here in Washington State, another one in Louisiana. I work at Caltech, but we also work with MIT. So we have employees at different institutions working at the same sites in different states, et cetera. In addition to Caltech and MIT, we have a collaboration of scientists in various places at other universities that we work with. So we're also multi-institution. We have UW Milwaukee providing compute resources, and Syracuse University, and the Albert Einstein Institute in Hanover, who also has an instrument, works with us, and so on. Plus scientists around on the order of 100 other institutions around the world, which also makes us international, which makes for some interesting things like export laws. Plus, it gets really interesting trying to schedule a teleconference that everybody can make at the same time. So, that makes it interesting for us. We've also, because of this collaboration, we had a lot of people different places wanting to make resources available to other people. We're not all at the same place, so we don't all have the same credentials. We actually build our own authentication infrastructure. So we already had this single sign-on service that we built, okay, that we like. It uses Kerberos for authentication, okay, and Shibboleth for authorization. And then we use Grouper for group management. There's LDAP on the back end that glues some things together and so on. This works really well for us too. But because of this, we also wanted to leverage this for what we're doing. So, you already know we also have a one-time password system. The reason we ended up deploying this in addition to our existing infrastructure is we had some things we were worried about, and our security policy says that if we're going to deploy a security mechanism, we need to be able to explain the risks that it addresses and why we need it. So we don't just put things in because they sound good without actually thinking it through. So I'm going to walk through a little bit of risk analysis, what we have at risk, and what we're worried about. So unlike some organizations, we're very open. We do open science and we do open data. So we don't have the confidentiality requirements that some places have. Right? People can have our data for the most part. They can have most of our stuff. So we don't worry about secrecy so much, except in some limited cases. But we're collecting data from astrophysical phenomena, which means we can't repeat an event that happened if our instrument happens to be down when the event happens. Basically, there are no do-overs in what we do, and it's time critical. The instrument has to be running when we need it. We want it to be running for certain lengths of time, etc. It's hard enough making this system work, even without the computing part. So if we can keep our computing systems up, it's important, or it makes things that much easier. We also have remote access to our instruments and to the control of the instruments. In our environment, we have to. We got facilities in different places, and sometimes we have one expert that needs to be able to troubleshoot problems in both places at the same time. There's no way we can just require people to only be on site to do certain things. As I mentioned, we already have this common sign-on across a single and in some cases single, in some cases just common sign-on that we provide to all of our users at different institutions. But that means that we have users who have this one password, but they're entering it on a whole bunch of different systems, service providers, at different institutions being managed by different people. Plus, we can't stop our users from taking the password that they have for our institution, for our organization, and using it as their same password on Gmail or other places where it could also get exposed. So in the end, we're allowing remote access to our critical systems from machines that are not necessarily in our control, people's laptops, their home machines, etc. Those machines could get compromised, or one of the service providers they use gets compromised and their credentials get stolen. So one of our outstanding risks to control this instrument is credential theft. So we have other risks we need to worry about, but one thing that I can't stop and I can't necessarily detect until it's too late is somebody stealing a password and using it to access our critical systems. So we decided to address that. I mean, we could just, well, there's a variety of things we could do. The first thing was we said, well, okay, we need people to have at least a separate credentials so that if it's not, if their password they use for their mail and other things get stolen, at least you can't directly use it to log in. And part of what was driving me with this is experience I've had in incidents in the past where an attacker would Trojan SSH, get passwords, and then immediately go see where else he could use those passwords. So wanted to have a separate credential, but since even that credential could be at risk from, say, a compromised import or something, we also wanted it to be non-replayable. So even if somebody does manage to intercept this password, this critical system, they still wouldn't be able to use it later on. And I want to make a point that we're talking about one-time passwords and not just two-factor authentication, because there are some two-factor systems that are replayable, such as X509 certificates. So the other thing, though, is we didn't want to have to require it for everything. I said we should be using this for the systems that are really important and not requiring people to use this just to be able to check their mail, etc. Now, you could argue about that point. You say, well, maybe you really should have everything. There are important things in email. But in our environment, I'm not as worried about that. Plus, I thought it was better to emphasize that the token is really important for critical systems, to emphasize the point that these systems are really important. So the fact that users have to use those separate from their everyday stuff kind of reinforces that notion to them. So, like I said, basically we got to the point where we're talking about one-time passwords where the user uses a new password every time they authenticate. And then if it's intercepted, it can't be used by an attacker. It is important to understand, though, that one-time passwords don't solve every problem. They're not a panacea. They don't solve all your security problems. Like any security solution, they only address a particular set of problems, and usually only that set of problems. And people often get kind of conflate what problems they do and don't solve. So I wanted to talk about it a little bit. The main thing that OTP solves is replay attacks and easy sharing of accounts or credentials. When I say easy is that I could still share an account with somebody by giving them the current one-time password over the phone or something like that. It doesn't really prevent two people from using the same account, it just makes it annoying. Okay, but it's important to understand the things they don't solve. One-time passwords don't provide authorization. They don't solve the authorization problem. They only give you an authentication method. They don't protect you from session security problems. A session can still be hijacked. An active session can still be hijacked. Okay? And what kind of goes with that is they don't protect you from a compromise of either endpoint. I like to emphasize this all the time because people say, "Oh, well, we're using SSH keys, we're using whatever. We don't have to worry about anything being compromised." If the attackers compromise your laptop, they've got your SSH key. Or even if you're using a token, they can hijack your session, right? We actually don't have any solution for endpoint compromises, and I'm sure somebody will come up and try and challenge me that at the end of this talk. So a brief little bit about general stuff on one-time password types of one-time password authentication that we use to make our decisions. There are time-based systems where there's a unique password generated based on the current time, and also with some sort of shared secret using some sort of algorithm. I've used a token in the past that generated a new number once a minute, had an LCD display, just the number changed once a minute. So the password is kind of a one-time password, and some systems that password's still replayable for that 1 minute window. Some systems, once you've used it, you can't use it again for that minute, which means you can authenticate no more than once a minute. On some time-based systems, it means the client and the server don't have to keep track of what was previously used, or the server doesn't have to keep track of what's previously used. It just has to know the current time, which means the client and server, the token and the server, need to have their time synchronized. And you also have clocks drift, so you have to have a resynchronization process. It also means the client has to keep track of time, which means it needs to be some sort of a power device. So if you have a hardware token, it requires a battery. It'll have some limited lifetime, both based on battery, and a lot of them there's a limit to the number of tokens they can go through. So at once a minute, you run out at some point, whether or not you use it. The token I used before had a lifetime of about 2 or 3 years, and then you just threw it away and had to buy another one. So there are sequence-based tokens which don't use time, but every time you use it, it generates a new password for you. You press a button or do something like that. So basically, they're a pseudo-random number generator. They have a seed, which is the secret stored on them, and then every time you press it, it makes another call to RAND, you get another number. So each password generated is basically based on how many previous passwords were generated. So the client and the server have to keep track of that number and generally have to be in sync, right? The server has an idea of what is expecting, and the client is supposed to present that next one, which means if they get out of sync, which can happen, you also have to have a method for resynchronizing them. So for those, at least on some of them, the lifetime is limited by the number of times, again, number of passwords, but it's limited by the number of times you use it. If you use it 100 times a second, you're going to run out of them pretty fast, but you could use it for 100 years if you only use it, once a day. Something like that. There are challenge response systems where the server presents some sort of a nonce. The client hashes or encrypts that nonce with a secret node, sends it back to the server. The server also knows the secret, checks that the client used the right secret. These typically don't require synchronization. The client only has to know the secret. There's no index or time to be kept track of. Potentially unlimited lifetime because the server just generates new nonces as needed. And all that. There's also the classic one-time pad, which is just a sequence of pre-generated numbers. It's the one method where you can use a true random number generator to generate all of your passwords. The client and the server then have to be able to store all of them, to keep track of them, and keep track of which ones they've used, so they have to keep in sync. Your lifetime there is limited by the number of passwords you've generated. Now, just to differentiate, so I'm going to talk about token authentication because that's what we use. We're using a one-time password token authenticator. One-time password does not automatically mean token, and token doesn't have to automatically mean one-time password, right? So where we're talking, the token, in this case, satisfies the something you have and something you have. Typically, it should be a physical device, something you want to have be tamper-resistant or at least tamper-evident, and so on. And the reason I said they're not always the same as a one-time password and vice versa is you can have a token that has a certificate on it and just authenticates using the certificate, right? And you can do OTP using one-time pads, using a software client, which some people try to call them soft tokens. I think that's like really overuse of the word token. So tokens solve some problems, but again, not everything. What tokens solve for you is, one, easy sharing of credentials, at least in tokens that require you to physically do something with them. Means it's really hard to share that with somebody else at the same time. A secure token, a secure hardware device, should make it very difficult to steal the secrets from the token, the one-time password secrets from the token. They can let you be relatively OS and software independent and not require any dedicated software on the client. The things they don't solve, they still don't solve the endpoint compromise problem. They also engender some problems. We'll get into more details later, some of the issues dealing with tokens, but one of them is you can end up with a whole keychain full of tokens for all the different systems you need to get to. And that can be a potential problem or nuisance. It was an issue for us, as I'll talk about. So some of the usability problems in general dealing with physical tokens. The first one is, how are you going to get them to your users? It's not so hard if you're all in the same building or all in the same city, but it gets interesting when you're in different states and in different continents. Right? It also gets interesting when they break. So what do you do when somebody is on travel and their token dies? We like to say this is the Rolf problem. So Rolf is one of our key engineers. He's been with LIGO a long time and been key in building our interferometer. So he's the kind of guy that if something breaks, he might have to get up in the middle of the night wherever he is, whichever country he's in, to log in and fix things. So throughout our evaluation of this thing, we would continue to say, well, what happens if Rolf is on travel and X? What happens if Rolf is on travel and he drops his token in the toilet or runs over it with a car or something like that, or he's just forgotten it, etc. So for time and sequence-based tokens, synchronization can be a big issue, especially in this distributed environment. Does somebody have to physically come in to resynchronize their token? Can they do it on the fly? Do they need special software, etc.? So that's something you really got to take into account when you think about how you're going to support this stuff. And in general, support's a big issue. People talk about tokens in terms of the cost of the hardware. I'd argue that the cost of the hardware is cheap, regardless how much the hardware costs. It's how much does it cost to run the infrastructure, and even more important, how much does it cost to provision tokens, get them to users, support the users, troubleshoot problems, all that sort of stuff. That's a place where I think the thing that really gets overlooked in a lot of environments. We'll just use this thing, and then it becomes a nightmare for everyone involved trying to actually get them work and keep them working. Years ago, I had a SNCC card as a little challenge response device. And every time so it was a little thing with a keypad, you get a challenge from the server, type it in, get a number, type it back into the login prompt. And every time I used that thing, I ended up having to resynchronize because something was wrong, or couldn't get the pin to unlock the keypad to work, etc. So all of these things are issues, especially when users are complaining that they can't get their work done and it's time critical because their token's not working. So there's also you also think if you have existing infrastructure, how does that integrate with your existing infrastructure? Are you going to need a whole nother authentication system, another password database? Is it going to run separately, completely independently, or does it integrate with what you have? And one place I was, after a compromise, an IT guy just went out and bought a token authentication system without talking to anyone and said, this is what we're going to use. And it didn't integrate with anything that we had. If we'd had a conversation about it, we could. There were other technology at the time that would have integrated very well. But we ended up basically running another whole parallel authentication system just to support that. And what goes with all that stuff, as I kind of mentioned before, is different failure modes. Is you need to think about how can you deal with the failures. Failures of the tokens, failures of your authentication server, what happens when the network is out, what happens when the user has failed, etc. So to get through these things and to sort it out and come up with a solution that we really thought we thought out well, put together a committee. We like to do that at LIGOs, form committees for things. So we told the committee that their charge was provide strong authentication. We want it to be general purpose enough to be useful for a variety of services. So we don't want to come up with one very tightly focused solution and have only good for that, and then we want it for something else that wouldn't work, and we had to come up with a different solution or change everything. And that they had to take account the usability and support so that it wouldn't be nightmare of everyone. So the committee came up with a set of requirements, the solutions. The first one was, wanted to have one token for everything. We didn't want people to have one token per site or one token per service or anything. We wanted to be a physical device, not a piece of software, because we didn't want something that could be compromised, especially remotely. Right? We didn't want something that if an attacker got in your system, they get the secret and be able to use it. That kind of kills the point of having a secure authentication device. So that speaks to specifically running a piece of software on your laptop that gives you the one-time password to log into the service from your same laptop means that you're not quite getting the point. Because if your laptop is compromised, they've got that password. You might as well just use regular passwords at that point. So one of the arguments is, well, why don't we just use our authentication software on our phones? Because that's a hardware device and it's a second factor. It's not your computer. I think it's not much better. Has anyone heard about WireLurker? It was in the news last week. And there was another more generalized case of it this week that I can't recall, a mask attack, I think. So in short, WireLurker was an attack where they compromised people's Mac computers. And once compromised, when the person plugged their iPhone into the USB port to sync it, they got the device ID and the user's email address and all kinds of identifying information off the phone, which means now they could pair the user's phone with their computer and identify what phones to attack. And they installed malicious software on the phone using an enterprise, can't remember the exact term, enterprise development certificate. Apple has a means where you can get a signing certificate for your iPhone app that doesn't require you to put it in the Apple Store. It's to be used within your organization. But any phone will accept an app signed with any enterprise certificate. So it was relatively easy to get malicious software onto people's iPhones without them knowing. So now they know what your phone is, and they can have it sending stuff back to them whenever they want. So one of the things I said when we had this discussion about what we were going to get, I said, I want to do this once. I want to come up with a solution that we like, but not have to redeploy it in a couple of years because the system we put it on has been shown to be compromised. So, wanted to be a hardware token. The other thing we wanted to do is minimize what had access to the secrets. We didn't want to have to trust services or service providers with them. So some solutions, there are one-time password solutions out there that just make use of PAM. But that means you have to tell, in fact, that was one of the things that was, somebody originally put up as a proof of concept. But that meant every service provider had to know the secret to the user's one-time password, which means that if any service provider got compromised, the attackers would know all of the secrets for all of the users that were provisioned for that system. So we didn't want to have to trust service providers. We also didn't want to have to trust some sort of third-party service to do our authentication for us. About the time we started talking about this, a large company whose business is to sell tokens and authentication service to people, whose name I won't mention, but it was 3 letters that may or may not also identify an encryption algorithm. They got compromised, and basically all the secrets got stolen off of their servers because while they had maybe a pretty secure physical device, they had really shoddy system administration processes and really shoddy handling of the actual authentication information at their site. And I don't want to have to deal with arguing about what the liability is there. I wanted to basically own the thing and not have to worry about somebody else doing something stupid that I had no knowledge about. that basically it becomes impossible to assess the trustworthiness of third-party organizations like that. In our environment, we had to be distributed, multiple sites, and we need to be fault tolerant because we have network outages. Jonathan will make mention of some of those things later on. And also fault tolerant, which means these things had to work when the full network wasn't up, and also be able to resync properly after failure, etc. We also need to be able to have our authentication nodes wherever we need them to be, if they need to be co-located with a service, but also be able to access them remotely. We want to keep things as open as much as possible, make use of open standards wherever we could, partly so that we can make things pluggable and be able to switch in between. If something became vulnerable, we could switch to something else. We didn't make open source a requirement, but it certainly seemed desirable because we could vet code, and it needed to be low cost because we're publicly funded, so it's not like we have a lot of money to go around. And the cheaper we could make it, the easier it is to have as much of this as we need, and so on, both in the hardware costs and in the support costs. We want to be able to afford to give tokens to everyone who wanted them and not kill our system administrators in the process. So we ended up with, in the end, we ended up with a custom authentication server that we built ourselves, which uses a custom PAM client installed on the service providers. The token we came up with is YubiKey. It's not the only solution out there, but it's low cost and it met our needs pretty well. And from what we've pounded on them a little bit, and they look relatively secure to us. We already had Kerberos, so we made use of that as the other factor in the system. So we had a two-factor system. So you have to present your one-time password and your Kerberos password, so that if somebody steals your token, they can't use it without also knowing your Kerberos password. So this all integrates well with our existing infrastructure. So the classic question is, why did we roll our own? The main reason is we really wanted to have our infrastructure on site. We wanted to have ownership of the system, and we wanted to be resilient. We didn't want to be dependent on someone's cloud that was going to go out on their schedule, not on ours. And as if it's one less trust relationship that we have to worry about. These are secrets to our critical systems. Why are we going to trust somebody else with them? We wanted to avoid trusting black boxes where we don't know how they operate, and we came up with the term with black clouds for clouds that we don't know what they're really doing on the inside. And the other thing is, as we looked into this, the idea of a multi-site, multi-institution, single token solution is not really a common model that's being addressed by most people, and we didn't want to have to require the users to install some sort of proprietary software on their computer, especially since they don't all even work in the same institution, different support models, et cetera, et cetera. So that was kind of our decision process that led us to this. And Jonathan, who actually built our infrastructure, is actually going to talk about how it actually works.
Well, there's, as Abe has talked about, we looked at a few different models and a few different systems for this. And some of the things that were very important to us was to have an open and a vendor-neutral solution so that we didn't get stuck with a single supplier. And we wanted something that we could understand. Now, there are a few ways to approach this. As has been talked about, there's a fairly common model right now where you put everything in a third party, out in a cloud, out on the network, some remote data center. It may be a distributed system that has 5.9 uptime, but it's still, from the point of view of an individual organization, it's a single point of failure that's not connected to your system. It has a few conveniences. You don't have to maintain it. You shove money one way and you get tokens back the other. But you have to, you're limited then to your connection to the outside world, and also relying and putting all your authentication and authorization secrets into someone else's hand. Another model is to do everything locally, and there's various levels of sophistication, going down to having an authentication server on every single service provider, with or without replication of data, and that just doesn't necessarily scale. What we ended up with is a mix between that. It's not a fully distributed system. It is centralized into a number of authentication servers that we distribute geographically around the United States. And so this gives us redundancy as far as multiple network paths, multiple sites that are very redundant, and we own it, which is nice. As Abe mentioned when we were discussing this, one of the large security vendors was being compromised, and I don't claim to have better resources than they do, but I do have my own logs, and I can be sure that I'll look at them when there's a problem. One of the things we see with this is we're not necessarily large as far as in number of people, but we are very distributed and we have lots of different groups. And so we have to look at how can we support them and how can we get access to everything. And one of the things is we put these servers around. How does that scale? We have one. That's very easy. We don't have to replicate anything. It's a master copy. 2, we have to start replicating data between them. 3, it becomes more complex. And we can scale this up, and the limiting factor is how quick do we replicate data between them. In general, you want your data to replicate as quick as it possibly can, because that leads into prevention of replay attacks and other things. And we'll talk about that. But one of the overarching things we really wanted to look at is we have to survive failures. Being a research project spread across the U.S. and with collaborators across the world, things fail. The network is largely reliable, but we have things that take the site down and things that take individual services down. Probably the more interesting of that is in our Louisiana site. The site is located on what was historically a hunting ground, and a very lucky shot nicked a fiber that was hung above ground, and when the wind blew one way, the network worked great. When the wind blew another way, there was a lot of errors coming in. It drove our local administrators crazy. We've had transformers blow up from birds and tumbleweeds in the eastern Washington desert. And so we designed this with the understanding that things fail. And so we need to be able to survive that. And one of the basic premises is that each system should, if it can reach any authentication server, should be able to work. So work as long as you can reach anything. And so we don't have a system that's a one single instance, maybe running distributed, that requires that you have a quorum of servers up that do multi-server locking. We look at it as being a integrated network that can split and join as circumstances demand. And another look at architecture. As I mentioned, we looked at how things connect together. Each of the service providers connects into our system through a PAM module or through Kerberos, and those will talk to an authentication server. The important thing is they can fail over. If the local one fails, they go offsite. If that offsite one fails, they go to another, and so on. And the actual service providers need to know very little. They just have to have the bridge, which is most commonly for us a PAM module that we wrote. And we'll stack it with others to provide different forms or different layers of authentication. We also have an implementation that can do a KNet with our one-time password. That's not widely rolled out, but we have implemented it and have looked at the challenges that brings in. One of the most important things with a distributed system with a one-time password is you have to replicate the data. When you look at an oath token, which is what we used, you have two pieces of information. You have your secret and you have your index value that tells you where in the sequence of 1 times passwords you are, and that has to get around to the servers as quickly as it possibly can. And replication takes time. When you have servers located across the country, you can measure that time. What we have done is to work out a system where we downplay the importance of replication. We don't need to try and lock servers across the country. Each token is assigned a home authentication server, and when the network is up, the authentication server will receive a request, say which token is this. Okay, this goes to server A or to server B, and send off the request there. And then that server will validate the authentication and update the database as needed. And then you sidestep the issue of having to replicate the data very quickly, because the home or master server for each token doesn't have to receive updates to know that it's valid. You still need to replicate because you need to get that data around, and that helps with your failure modes. When a system fails, a non-home or non-master server is allowed to authenticate any token, but we require it to do a double authentication. Since we can't reach that master server, we can't guarantee that a replay attack is not feasible. We just mitigate that by saying, please give us 2 token values, or 2 one-time passwords. So to summarize it, it's a centralized system, but still distributed geographically. We do not require endpoints to maintain secrets. There's only 1 token. It's a modular system. We base it on open standards, so we can plug in any token, any vendor we want, as long as we can understand how to seed the token and have code to generate the one-time password. We provision the users, and it's one of the challenges we've had. We're distributed. We will bulk provision tokens, and we'll send them out to large compute centers we have. We want to make it simple. So we have them prepared. We mail them out if we need to. These are hardware tokens that are relatively hard to extract the secret from, so we can safely mail it to people. But it's not tied to anyone until they receive it and activate it themselves. So we need to make this distribution something that's safe, and which is the reminder that authentication is not authorization. We try and make the support as easy as possible. Any authentication scheme is a hindrance to users. The basic idea is if someone has a problem, we just tell them to replace their token and go to our support portal and take ownership of the new token. Our experiences with it over the last few years is it generally works. That makes this slide very boring, and that's a good thing. Tokens get out of sync. This is one of the somewhat common things we've seen. With a YubiKey, you have to plug in the device to power it and then have to activate it, and so it takes a lot of effort to get out of sync, but determined users can. When good tokens go bad, these things are actually fairly rugged, and we haven't seen it. We thought we had, but it was a bad USB port. And then local account issues were distributed. The group that does the central infrastructure for the accounts isn't the group that does the SPs. And so they don't want to have a fully automated system where someone on the other side of the country pushes a button and they're granted access to our most critical systems. So that actually has been our biggest problem. We could automate it. They don't want it. We have a Kerberos solution. We like single sign-on. We can't afford to support all the different client systems that come our way. And we can't wait for the OTP extensions that are in the draft standard to come through into the client systems. So we hijacked the encrypted timestamp system. Every KNet supports this. No client modifications. We just have to modify the KDCs. And there are several orders of magnitude less KDCs in our organization than there are users. This is easy to support relatively. Questions?
Go ahead.
Can you discuss what specific software versions you're using and what modifications you're doing to them?
You mean for Kerberos or for everything?
Well, I'm assuming that you're using MIT Kerberos. I'm wondering how you're...
We're using MIT Kerberos. Our KDC patches against the 1.6 release. The rest of it is custom code. Our database that we use for replicating it, we use CouchDB, which gives us master-to-master replication and some nice failure modes.
But just to be clear, our production system actually uses Kerberos without any modifications. So when you authenticate to an SP, you get asked for your token code and then your password, which the SP then uses to authenticate to the KDC. But we have working code that allows you to key-init using your token and then just use native Kerberos clients and all that. That doesn't require any modification of key-init. None of the client-side Kerberos software just requires modification of the KDC.
Hey, my name is Brad Tilley from Virginia Tech. Curious, when you were researching this, if you looked at HOTP or TOTP, the Oath RFCs?
Yes, and we tested it with both the time and event-based systems. Principally because of YubiKey, we used it in Oath mode with the event-based HOTP.
Thank you.
But we're not limited to one particular token or algorithm.
Yeah, Oath works well for us now, but we wanted to design something that if Oath ends up being broken, we could easily switch to something else.
Thank you for your time.